International Perforating Forum webinar. First, I would like to give you some information on the webinar format. You should be able to see the screen being shared and hear the audio, but your microphone will be muted during the whole webinar, including during the Q&A session. It's important to connect to this event using Google Chrome, as other browser might just not be compatible, and the webinar performance will be affected. We will first have a quick 5-minute introduction on the CE chair with the IPFC. We will then proceed with the actual presentation for about 30 minutes. After that, we will have 15 to 20 minutes on a Q&A session. Please keep in mind the webinar is being recorded and will be available on the IPFC website, which is www.perforators.org. You can submit your question anytime during the presentation, and they will be answered at the end during the Q&A section. We will give you about 5 minutes for the participant to join before we start. And I can still see people just joining us, which is great. And it's a great start of the year for IPF and for the first webinar, I guess. If you know of anyone who has any issues registering, just send us an email, and we'll redirect them to the right link. For the ones that just joined us, my name again is Eliana Madujano, and I just wanted to inform you or give you some information on the webinar format. We should be able to see the screen being shared and hear the audio, but your microphone will be muted during the whole webinar, including during the Q&A session. It's important to connect to this event using the Google Chrome, as other browsers may not be compatible and the webinar performance will be affected. We will first have a quick 5-minute introduction on the CE chair with the IPFC. And then we will proceed with the actual presentation for about 30 minutes. After, we'll have 15 to 20 minutes on a Q&A session. And please keep in mind the webinar is being recorded and will be available on our website, perforators.org. You can submit your question anytime during the presentation, and it will be answered at the end during the Q&A session. I think we're about to start in about 1 minute, so I'm just gonna wait for other people to register.
How many have you got now?
Okay. $31 so far. All right, I think we're ready to start. I would like to introduce you to Carlos Guedes, the International Perforating Forum Continuing Education Chair. Carlos is the Perforating Portfolio Manager and Product Champion for Schlumberger. He has 15 years in the oil and gas and has been involved in different positions, from being a field engineer to several management positions in sales, marketing, and operations. Carlos is also a member of SPE and a participant of the API19B and RP67 subcommittees. Carlos, thank you for joining us this morning.
Thank you, Eliana, and good morning, good afternoon, and good evening, everyone. It is with great enthusiasm that I welcome you to our first International Perforating Forum webinar. This webinar is an initiative of the Continuing Education Chair. The Continuing Education Chair mission is to disseminate technical knowledge about perforating to industry professionals and students. The webinar is a new way to share knowledge, and in my opinion, is a much more dynamic way than what we have done before. If you would like to present in one of our webinars, in the future webinars, we would love to hear from you. So you may contact us at webinars@perforators.org and tell us about the topic you would like to present. I also invite you to visit the Continuing Education Chair webpage on perforators.org for detailed technical information on multiple topics on perforating, included a selected list of SPE publications. Well, enough about the Continuing Education Chair introduction. Let me introduce you today to our webinar presenter. I am honored to have Mr. Mark Brinsden as our first presenter. Mark Brinsden is the president and founder of Vektor Energy, a technology consultancy. He has held several positions since he first joined the industry 39 years ago with Schlumberger, followed by Prodrill, Expro Group, and Shell. After leaving Shell in 2018, where he was principal technical expert in perforating, he founded Vektor Energy to progress his passion for technology, especially in the areas of energetics for enhanced production and well integrity. Mark has invented several perforating gun systems and is currently working on applied energetics for well control and well integrity. Mark received his bachelor's from Edinburgh University in geology in 1979. Mark is also founder and current president of the International Perforating Forum. Mark, welcome and thanks a lot for being with us today. The floor is yours, and we are excited to hear from you on the API19B topic.
Well, thank you very much, Carlos, and thank you very much to both of you, Eliana and Carlos, for all your efforts in making this new webinar series happen. It's very, very interesting, I think, that we now have this possibility of expanding out to this new form of communication for IPF. I'd also like to thank the IPF for the opportunity to do this. This is a great opportunity. And hello to everybody around the world who have kindly logged in. I do hope everything's fine with you. So this presentation is not on behalf of the API, and I just want to make this clear disclaimer that we make these presentations on our own behalf as individuals. But I was a member of the API19B committee since about 2006 and chairman since 2010. And I feel I was fairly responsible for making the changes and bringing forward the kind of improvements that we needed to change the standards. What's really important is some acknowledgements in this industry. And I think this is really something I want to push quite hard. It's all about voluntary efforts. There are so many people, engineers working for operators and service companies and manufacturers, and they all make it possible for us to have this high quality of API standards. And it's a huge amount of work has been going into this over the last 5, 6, 7 years in making this new standard. So let's be very, very clear. This is down to individuals who give their own personal time to make things happen. And I'd like to think of how all of you out there can also help deliver standards with the API and other standards organizations, and also quite importantly, volunteer with groups like the IPF and the SPE, and those kind of industry bodies. Volunteer participation is so important. Okay, this is another acknowledgement, just a picture of a group from our API subcommittee meeting back in 2018. We don't always take these pictures, so this is the last one I had. And there's a lot of people go into making this all happen. There are now 3 API committees that are working. Apparently, I'm not quite loud enough. There are now 3 API committees involved with perforating. There were 2, but in the last 18 months or so, we started another one. And the one that we're going to be covering in this presentation is the API RP19B. There's also the RP67, the explosive safety recommended practice. And this covers all aspects of explosive safety. And the new edition now comes out with a major increase in scope and is much more comprehensive and detailed. And I do hope that we will get a chance to have a webinar on this topic as well in the next few months, and I'm sure we will. There's also another new one, which is a specification for downhole perforating tools and related equipment. And this kind of came about because people were noticing that we were going to higher pressures and things like that, and they wanted to make sure that the tools were performing as required, and that the standard was being maintained. So it defines a minimum standard for reporting, validating operational ratings of perforating tools that are not actually covered by any existing standards. It covers things like perforating gun materials, connections, seals, cutters, etc. Okay, so the presentation today is going to be an introduction. We'll talk about measuring perforator performance traditionally, and recognizing why it's important to measure perforator performance. And then look at the new API19B and how that's changed from the original one, and look at some conclusions and takeaways. For example, the old benchmark for indicating perforator performance in wells was a surface gun test. It's an API concrete block, and that was great. And it created a very consistent sort of result that everybody can compare gun to gun with. However, we found that as operators, we found that the API concrete target was not really representing what was going on downhole. And we couldn't get any real correlation between the concrete target and actual downhole conditions. In downhole conditions, we have overburden, reservoir pressure, and rock properties that all have a big impact on penetration. And so as we were starting to work on more difficult reservoirs, we found that we really needed to find a way of selecting charges based on actual performance. And some of the concrete contractors, including my previous employer, worked a lot with contractors to design and manufacturers to design charges specifically for their own more difficult fields and the reservoirs and the rocks, etc., in those fields. And from the contractor and manufacturer point of view, if they'd already, spent a lot of time building these, designing and manufacturing these new concrete-based charges to perform well in surface concrete, there was a little bit of reticence to move forward with this for a little while. But really, they were very good once they sort of realized that this was going to happen. They all pulled together very, very well. And with a lot of effort from contractors, manufacturers, and operators, we now have new standards which are being written to promote shots into concrete stress targets as the main standard for identifying the kind of performance we might expect in downhole. All the major standard manufacturers have now dedicated facilities, which is really important. Okay, I'm still getting issues about not clear enough. All the major contractors have now dedicated facilities to provide stress rock tests, and that's an amazing accomplishment. A lot of effort and time and money has been put into this. And the last 5 years have seen significant developments in technology with contractors and manufacturers working effectively to improve performance and technology. It was very good when they held the mic up. Okay, it's meant to be very good all the time. What we were told originally, looking back over time, over the last 10, 15 years, is that let's just go. API penetration is measured in. So we're discussing now why API penetration is measured in concrete, not rock. So rock is really the best target, but we were told it's very expensive and not repeatable because, for example, when we take a Berea sandstone target, the Berea we were getting at the time was very inconsistent, had different porosities and hardnesses, etc., which resulted in very different performance. But concrete was seen as a very repeatable target, and they even changed the concrete design to a 1630 frac sand target, which is also a relatively reasonable cost. And there's a large database of performance in concrete, so everybody was really pushing towards that. So it's very, very convenient for the contractors, but those of us in the operators group were finding that, we really wanted something to tell us more about what was going on downhole and how to compare charges from different contractors and manufacturers, and rather than just going on the concrete performance. For us, it was, as operators, very important because perforating is the only real connection to the reservoir. And it was really important to get that perforation right so we get the good well performance. But only API section 1 concrete performance was available to compare charges. But it really wasn't good enough, and we really needed something better. And about 4 years ago, we inserted this statement here: penetration data recorded in API19B section 1 may not directly correlate to penetration downhole. Just to make sure that people were aware that the general consensus in the industry was moving away from a concrete target towards understanding what was really going on downhole. Now let's look at measuring perforator performance in section 1 as traditionally how it was done. This is a little picture here below of the target with the casing, and the concrete was set for 28 days to create a consistent strength. It had to be above 5,000 psi compressive strength. And you can see on the right a picture of shots going as the target is split, the nice clean lines from the shots going into the target. So while we don't really think it's very good from a point of view of penetration in downhole conditions, it does give you a fairly good overall indication of the charge interference within the gun and indicative range of perforator performance, because sometimes when you look at the charge data sheets, you will see that some penetrations might be 50 inches, and on the other hand, some might be 25 inches. And so while the average might be 40 inches, the actual variation is quite considerable. And that gives you an indication of kind of quality of manufacture, perhaps, of the charge. But also interference is a big issue because if the gun's designed incorrectly, charges can interfere one to the other and block or disrupt the shot. But as we said, it doesn't produce a significant indication of penetration in downhole conditions. Interestingly enough, this is a graph that was used way back in 2000 to demonstrate why concrete to rock correlation was sufficient for use. As you can see, there's a nice straight line through a dotted charge results. And however, when you actually analyze it a bit more detail, you can see here in the blue lines, for example, that 10-inch penetration in Berea as 18 inches in concrete. That's not looking too great. And then for the same charge in concrete, it's 15 inches, 18 inches in Berea. So we were really getting an issue there with relative performance in rock to concrete. The next test, which was very useful for the development of charges for rock, is the stressed Berea sandstone target. It's very often now used as a charge development tool, as it's relatively quick. It's quite easy to do several tests a day and adjust the charges and look at the performance in relatively good downhole simulated conditions. Then we have the single shot into a steel target in section 3 on temperature. It's very useful again for looking at performance at temperature. And then a very important one, section 4, where we have a single shot into a stressed rock target with fluid pressure and flow. Closest thing really to simulated downhole conditions, and enables us to flow through and backflow, and also look at things like gun volume factors, the way the pressure on the simulated wellbore side and the simulated gun chamber side impact the tunnel and how clean the tunnel is, etc. And then finally, section 5 was looking at debris and becomes very important, certainly in more complex completion conditions where we're very concerned about debris, especially again with big hole gun systems. Now, let's have a look at measuring perforator performance. So we were looking at how we were earlier on about the existing systems, and we wanted to find out why that is important now going forward for the difference between concrete and rock penetration. Here we have a graph showing 3 different curves of rock penetration in stressed rock against a rock strength indicator, which is basically taking confinement and pore pressure, the overburden confinement and pore pressure, and the impact that has on penetration for a rock target. And you can see that this is the same weight of charge, this is the same size of charge, and it's shot into in the same conditions for all 3 charges. And in certain conditions, you can see the old charge performed relatively well compared to a 2nd generation charge, and then how a 3rd generation charge might perform differently. So all these charges are the same weight, you know, they're can be run in the same gun, and they look identical, but they perform quite differently under different conditions. And so it's important for when, for example, you're deciding to use a more expensive charge, for example, that you are aware that the charge is actually performing significantly better under the conditions you're talking about. Interestingly enough, we actually look at the concrete penetration for these charges. You can see in red at the top, we've got something that's about 48 inches compared to sort of typical downhole conditions of, say, 12 inches. And then if we look at the oldest charge, you can see there it's about 35 inches compared to typical downhole conditions of about 8 inches. So it was really important that we get away from just seeing these wonderful 50-inch penetrations and thinking that's what we're getting downhole, because it's not what we're getting downhole. It's more likely to be somewhere between 10 and 20 inches in reality. There are now new extreme requirements for perforations in the HPHT wells and deep hard rocks and the very low permeability reservoirs, etc. So there's a lot of new kind of work that we're doing in the last 15, 20 years that wasn't being done when the last standard came out. So it really is time to do this. It's not really a case of just throwing some holes in the ground and hoping for the best. Let's have a look at some modeling. So up until a few years ago, everybody was modeling using a very little impact of stress and overburden, etc., and pore pressure on penetration. Whereas we were getting typically models which were showing that a 4,000 psi UCS rock could have a penetration which is higher than the concrete, which was, say, a UCS of 5,500. Because it appears that 4,000 psi UCS is less than 5,500. So, wow, there must be a better penetration. But in fact, it didn't take into account that the overburden pressure was 12,000 psi at around about 12,000 feet. So that 4,000 psi now suddenly became more like 10,000 psi. So it was really important that we take into account pore pressure and overburden pressure, especially in penetration. And things like porosity as well. At the time when we were doing our inflow modeling, we were finding that when we get data from contractors about penetration, we plug those into the models, and typically we would take a factor of about 30 to 40% of that penetration to put into the model. So we already knew that the models weren't telling us what we really needed to know. And to fix that, we were making these big correction factors in the models. However, once we developed some real models which took into account downhole conditions, then we found that we didn't need to make these correction factors anymore. So using, let's have a look at this, and you can see here we got 2 guns operating in stress rock. We can see that the inflow model on the right, that one gun has a significantly better advantage to other. And you can see that it's generally smart to actually do your inflow performance work based on actual either a very, very good model or some penetration data that you've taken from real rock data. So far, we can see that it was geared heavily in the old system was geared heavily towards using concrete as a consistent test material, even though it was not really any use for correlating downhole conditions. And there was a great ideas to generate things like low-cost synthetic target materials as well. But we decided to keep it as simple as possible going forward. Now, looking at the new API19B, new section numbering has been introduced, but we then managed to put in it in the same order, but in this case, we had a 4 before it. So 4.1 is now surface conditions, concrete targets, and is very basically the same as before. However, it's now allowing for mixed charge systems. So typically now we're seeing companies putting more than one type of charge into a single carrier. And also clearly states that penetration data recorded in API19B section 1 may not be directly correlated to downhole conditions. I felt the statement was weak and should really clearly indicate that there is no useful correlation between ambient concrete and in situ performance. So in 2019 in May, I challenged the use of this weak statement, and we had a unanimous vote, and it was decided to change the statement to something like penetration data recorded in 19B does not correlate to penetration downhole. So please take that into account when either you're buying or selling gun systems. But it really is going back to the importance of this section 1. It's a charge interference and relative performance, relative performance in the target system, and it's very, very important. We cannot do away with this at all. So the section 2 again is pretty simple and similar, and is great for giving us an indication of downhole performance. And it's a fairly quick and relatively low cost way of doing your target testing. And I would certainly recommend it. And most of the companies now have these kind of facilities. Now, all of these systems that we have, the different manufacturers and companies and service suppliers are different. And they have different ODs and different designs. However, detailed comparison test program was carried out 2 years ago and only finalized last year, which is instigated to ensure that all test facilities were able to provide consistent results. So a single set of rock targets were distributed from a single quarry run, and also a single run of charges was distributed from one manufacturer to all the facilities. I'm very, very pleased to see that the results were very, very consistent. And we decided there will be 3 tests under confinement pressures of 1500, 5500, and 9500 to simulate to give us a kind of curve to show the performance in the downhole conditions of a given target, charge in a given target. And to make sure of consistency, there'll be 4 shots in each target. And we will record casing dimensions, total core penetration, total target penetration. And this, for the first time, really provides a completely comparable data set for any charge. It's not perfect, but it's a lot better. And we can certainly improve, I'm sure, over time. But for the next few years, this will be the way we do things. What's important as well, for the first time, these tests will be officially witnessed and recorded just like they are in the Section 1 tests. Section 3 is the evaluation of elevated condition temperature conditions test. And basically, it's unchanged. It's a little bit more detailed. It was written more clearly, I think, than the last time. And we can now operate in slightly more elevated conditions. Section 4 is good because we've written up the standard in a far more detailed way, and it allows us to use it under more varied conditions. It's a really critical test, and it gives us a really clear indication of inflow performance in wells. And using this new standard, we are able to, make sure that the different test facilities come under the same conditions. So core flow efficiency and productivity index are the key sort of things that we're now able to get out of this. And there's a consistent way we are measuring these. How to do the calculation, how to do the measurement is clearly stated in the new section 4. So we have a consistent result coming out from all manufacturers and contractors. And as I said earlier, this is a test that's very important for showing how flow performance is affected by different dynamic conditions in terms of wellbore to reservoir and gun carrier volume. Okay, so finally we got the section 5 has been rewritten a little as well. It's does provide a reasonable measure of relative performance of different gun systems, and it's tested under controlled conditions. And sieve size analysis and things are in there as well. I'm rushing a little bit here. There's a new system that's coming out now, swell determination. We've had something like this before, but now we've got it really down to a much clearer design recommendation. The gun indicates the gun swell along 2 dimensions along the length of the gun. In this case, for example, a 2 7/8 inch gun or less diameter, we have this 18-inch no-go tube. And this is because we have a tendency in smaller guns for not only to swell, but to bend as well. Now we've got a proposed section 7 coming along. We were thinking of trying to getting it in this time, but there's still a lot of discussion going on about how to get this consistent and right and how everybody can agree on it. It enables us with one shot to take in different grades and diameters and weights, etc., of casing to be tested on one gun section. And that's a very useful thing because that's going to give us some very important information on relative hole sizes, burr heights, and the effect of gun clearance on shot penetration, and could also be shot in either fluid or in air. So let's have a look at the conclusions and takeaways as we wrap up here. There was this sort of clear acknowledgement after a while that using section 1 was not going to be able to be continued indefinitely, that we were going to have to do something new. And it resulted in a major paradigm shift in the kind of way the contractors looked at things. And they came up with a lot of significant costs. They have to handle a lot of costs involved with doing these numerous tests. So as we said, for a section 2 test, we're going to have 4 shots each in 3 different pressure conditions. And 12 shots is quite a lot of cost and time involved in doing this. And then you've got the cost of the target material as well. And so, congratulations to all the contractors and operators for making a huge effort to get their systems up and running and to agree to this new standard. Industry worked really well together with operators, and operators, few of us, very, very few of us, were around, and I'd love to see more operators involved in API in all 3 different sections to help push things through and ensure that there is some representation from operators. One other thing that's going on right now, API now sponsoring some work we're doing on time temperature, thermal decomposition, and stability of HMX. This is what we're doing with Lawrence Livermore National Laboratory using ODTX, which is one-dimensional time to explosion in those ODTX test cells. Complex offshore floater jobs are really where we're sort of going with this. So sometimes it takes an awful long time to run guns on completions, for example. And if we have to pull them, it can take us a lot of time. And then we could have weather conditions as well. And it can result in weeks, potentially, guns being in hole. So rather than just being concerned about what happens over 100 hours, we're now concerned what happens over weeks of guns being in whole at extended temperatures, borderline temperatures like 160 degrees centigrade, where HMX is kind of borderline. So we started carrying out this work, and the first phase of the work was completed in 2019. And we got this quite useful piece of information here on the right. And we could see that we had an explosion at 170 degrees centigrade there, and then 160 degrees centigrade. After several weeks, there was no explosion. We then extended that to 165, and we're now doing more tests on a different type of HMX, just to make sure that different formulations with different binders, etc., performed similarly. So we're repeating some of the tests in this particular area of 170, 160, that sort of area, where we're sort of pushing out the envelope of HMX. Okay, finally, looking at useful resources going forward for viewers here. The SPE has a great database of papers on perforating, so I certainly recommend you go there for your for a lot of up-to-date papers. API is the go-to place for your data sheets on charge performance, and so that has all been revised and updated, and I certainly recommend you keeping in touch with that. The IPF has a great perforating website called perforators.org, and that's going to show you a lot of perforating presentations. Every year we tend to have a couple of conferences around the world, and you'll see all those conference papers put up on the web. So that's very, very useful. And then we have a perforating safety database. I do recommend that if you are aware of incidents in the perforating industry, you can put that information up on the safety database. It can be put up in a way that doesn't show the originator, doesn't show the operator, but gives us the basic data, what happened, and what should we be watching out for ourselves in the future. So that database is very useful, and I certainly recommend it. It's the only one in the industry, and we need to keep that up to date. And then a couple of years ago, we started the Journal of the International Perforating Forum, and that focuses a little bit more on the deep technical side of perforating, the kind of stuff that probably isn't that suitable for the SPE, as it's very, very specific, hard technical stuff on perforating. And then now we have this new webinar series, and all of these things are free. So I would recommend you go ahead and get involved with the IPF and these other organizations, and enjoy learning about perforating and taking part. Thank you very much for listening.
Thank you, Mark, for a very fruitful webinar and presentation. We'll now move to the Q&A session. So for those in the audience, for the participants, if you want to submit a question, just click on your chat button there on the right side and type your questions, and we'll read them out for Mark. Okay. And we have a few questions here already, Mark. So I'll read the first one from Corey. It's a bit long. So regarding section 1, while the data that is listed on the data sheets can indicate some level of interference, there is no absolute indication of interference itself. There are data sheets out there that show as much as 50% difference in penetration, but most people just look at the average penetration and hole size. Do you have recommendations for how we can define what interference is and how it might be listed or quantified on the API section 1 datasheet? It's the first question there. So I'll let you answer that one, and I'll read the rest of it later.
Well, that's also two questions as well, I guess, isn't it? It talks about interference and then also the variation in penetration as much as 50%. I mentioned in the presentation that I'm taking an example that I often quote, where we have a data sheet for a 2 7/8" gun, which shows a penetration of like 48 inches and 25 inches in the same gun, in exactly the same gun clearance conditions. That to me indicates that the gun is not being, the charges are not being manufactured with the level of care and consistency that I would expect. Within charge manufacturing, they have to take a number of charges out every so many charges and shoot them in a target. You know, when you start getting these levels of variation, they should really be looking at what they're doing and why there is that variation. And I'm sure, in general, this system, this consistency is improving over time as charges are being more machine manufactured, and people are taking a lot more care on how the charge is developed. So manufacturing is a big issue. Now, what are we doing about interference? Well, interference is quite clear when we see charges that are shooting off at an angle usually, but we're not really inspecting, we're not taking that into account that much in section 1. And however, I would say on the whole that all the targets I've inspected over the years, I've seen very few, except with some big hole charges, that we've had major situation with charge interference with the gun designs they have. So in general, the companies, when they're manufacturing, take that issue out. They immediately see in their first test that there is an issue and they get rid of it. So we would very rarely see that. As I said, the only time I've seen significant charge interference with one company with their big hole charges. And they were working on it, last thing I heard. Going on, section 2. And what else we're going to do about interference? I sort of answering the end of that question. Well, I think the operators, the contractors, the manufacturers are all dealing with it, and when they see it, they fix their guns. Want to ask the second part of the question?
Second part is also if and when section 2 is updated, then a look at changing the casing used in this test should also be considered. So it doesn't have a question mark, it's a comment here. So if you want to make any comment on it.
Yeah, so it does certainly make sense that you should be using a casing, thickness, weight, hardness, etc. That is consistent with the kind of conditions being shot under, the kind of charges. I don't really have any other opinion apart from that.
All right. All right, we have another question from Mr. Hoffman. And the question is, given the differing geology of the target materials, has there been any consideration of applying a Gaussian envelope analysis to the data?
So when he's talking about target materials, he's talking about target materials and tests, I guess. Is that what you think he means, Carlos? Or does he mean in real downhole conditions in the actual reservoirs?
No, I think it's for tests. That's what I understand. We can pass on to another question. And
maybe ask him to just clarify what he means in a little bit more detail about geology of target materials. Does he mean porosity, rock hardness, UCS, confined compressive strength? What particularly are we talking about? Because geology is a kind of broad term.
Okay, he answered yes here. So.
Sorry?
He answered yes here, his comment. But Mr. Hoffman, if you can retype your question so we can read it clearly for Mark, I would appreciate that. All right, I have another question here. And I skipped the few questions above with names of companies and all of that, because that's not the intent here. So I'm skipping to Mr. Stefano. Is there an ongoing effort to validate and standardize how different softwares simulate performance? And here is penetration and hole size. Mark, you can read it again.
Is that really what it's saying? A single shot in real rock pretending stress rock so long. So
no. Here it is, Mark. Follow me here.
Okay.
Question from Stefano Caponi. Is there an ongoing effort to validate and standardize how different softwares simulate performance in terms of penetration and hole size? Is there any effort to standardize the softwares from the different alternatives in the market?
Absolutely not. Doesn't seem to be. We did try to get something set up. I had an initiative about 2 years ago to get everybody together to try and standardize a model for perforation models. So we have a consistent model used in everybody's own perforating model. So all these major contractors now have some kind of perforating model, which works fairly well. But certainly penetration, hole size, etc., is not consistently handled throughout these models. And so, yes, I wanted to set something up to do that. And there was a little energy to do it at the start, but it wasn't consistent, that energy. And I would really need to get some more individuals from the different contractors to come forward and say, yes, we as a contractor want to take part in creating a standardization. Unfortunately, my initiative didn't really take off that well. So I'm very happy to restart that initiative if we have the sort of main contractors certainly coming forward and saying we want to work together to have a consistent system. They're all adequate. I don't say anything's particularly wrong with any of them. If you want to know what the actual performance is, then do a test. My recommendation is, if you've got a new field and you're very concerned about the performance, then do some charge testing with your contractor or contractors. Thank you.
Thanks, Mark. So I have another question here from Servio, and I'll start from the middle of the question here. So Servio comments, a single shot in real rock, including stress rock, can't reflect some perforating phenomena like interference. We know that single shot performance could be different than multiple shot performance, which is more real. So how would we manage that with single shot tests in stress rocks?
How could we manage? That's not really.
Yeah, I guess he's questioning.
Okay, yeah. So we have the reality that you have single shot tests, or you have a section 1 type test, which the whole gun test. Well, let's just say first of all that generally speaking, if you have a typical charge orientation where charges are in a spiral, or you don't have a charge back to back, that the interference in a well-designed gun is not that significant. However, when you have back-to-back charges, that is very significant. So in the case where guns are designed where you have multiple back-to-back charges stacked up, then certainly in that condition, the backing up of the charge, it usually results in a slightly higher performance. And we can't emulate that. We can't simulate that. How else could we do that? We could maybe try testing the gun, the same charge in a section 1 test in a sort of conventional kind of spiral configuration, as well as a back-to-back configuration, and then take that result and then use that with the single shot to gauge the difference in performance between how we see it as a single charge and as a, say, a back-to-back charge. But in a conventional guns, which are not back-to-back charges, I don't really see any significant issue in interference.
Thanks, Mark. So I have a clarification here from Mr. Hoffman, and I'll read the question again. So if we deviate from concrete targets, like section 1, and start to use geologic samples recovered from downhole, then how do we normalize the inconsistencies in these geomedia? Okay,
right. We don't. I would say in general, in general, when we're taking targets that are from core samples, we take those as we have to shoot more than one target for a start, because obviously the core samples tend to be very variable. They're often broken. They're often heavily layered. We're obviously shooting along the length of the core sample, whereas in reality, we're shooting along the bedding plane probably. So it's only a guide. We can't expect this to do more than give us some indication of a better indication, nothing at all, of what's actually going on downhole. So core sample shots are limited in their ability to define what's going on downhole. But it's better than nothing. And So generally, we tend to take the average geology, average properties of the rocks that we're looking at downhole, and then we try and find an outcrop rock that best suits that, best matches that, and then we shoot that instead under the same pressure and overburden conditions as downhole. And that's what I would generally recommend as opposed to shooting core targets, especially those that are broken up and heavily layered, etc. They won't be very representative.
All right, thank you, Mark. I have one more question here from Mr. Conrad Ramirez. You mentioned that Section 2 tests will be witnessed, like Section 1.
That's correct.
Does this mean that Section 2 data will be made publicly available like Section 1?
That's correct.
You will?
Yes.
All right.
So right now, generally, if you go to a contractor and say, I want some Section 2 tests, they very well often would say, well, yes, this is how much it will cost you. It'll be quite nice to be in the situation where we get some consistent Section 2 tests as I outlined there at these different pressures, 1500, 5500, and 9500 PSI. And under those conditions, we can see the data. And that's not going to match exactly what you've got downhole, but it's going to give you a better indication of what's going on and what you might see in reality in your rock. Because the Berea sample that we shoot is not going to be the same as what you have downhole, but it will give you a better indication.
All right, thanks, Mark. I have one more question from Mr. Koresh. With the expanding application of digital slickline perforation, is there any plan to standardize the shock modeling and do some tests to verify the simulations for slickline perforating applications?
Sorry, the shock modeling? So what do you mean with the shock modeling?
He didn't specify.
Could you read it again, please?
With expanding application of slickline perforations, is there any plan to standardize the shock modeling and do some tests to verify the simulations?
I really don't see what we're looking at there. We're looking at shock modeling for the line as opposed to E-line. Or we're looking at the gun movement. Are we looking at dynamics? I guess we're looking at the impact of shock on the slick line. If that's the case, we already have shock models which take that into account. So I don't think that's an issue. Right?
Okay. So question from Mr. Servio. Mark, inconsistency and size are the main reason we could not use real rock obtained in the well. So that is why we need to look for an outcrop, but we need some consistency. Am I right?
I really didn't understand the question, but certainly, as I said, outcrop rock can be consistent. We can go along the bedding plane or against the bedding plane, depending on the actual situation downhole. We can try and match a rock as best we can to the conditions that we have, the actual geology. And as I said, the target material, if we take a core, as I said, it's often broken up. It's often highly laminated. It's not usually a very pretty target, and we can certainly pot it so that we can increase the diameter as we need to fit inside the test facility. But it's not usually going to be a great target. Sometimes you get great cores and you can use them, but very often the cores are not great and the consistency is very poor. I'm not sure if that answered the question.
I think it does, Mark. All right, I have one more question again from Servio. In the past, he has conducted a few single-shot API Section 4 tests.
Yeah.
But the investigation objective was to know which is the best technique to reduce perforation skin. Since a long time ago, there is a discussion on the best test to resemble downhole performance. I understand and I believe stressed real rock is the best test, but with multiple shots and using real hardware. Do you agree with that? And if so, how could we achieve that?
I found the question quite confusing. Could you reword it?
I'll read again. So in the past, he mentions he has done like 13 single shot tests.
Yeah.
Section 4,
Mm-hmm.
with the objective to know which is the best technique to reduce perforating skin. So his goal is to reduce perforating skin, and he's doing single shot tests. He has done single shot tests.
And he's shooting with
4.
variable gun dynamics, I guess.
Yeah, he didn't mention. Now,
Okay.
Now, he says that there is a discussion on the best test to resemble the downhole performance. And his belief is that stressed real rock is the best test, but with multiple shots, not with single shots, and using real hardware. And he's asking you, do you agree with that? That, for that skin study, is it better to do with multiple shot and real hardware instead of single shot test?
I have no idea what he means by real hardware, and I don't know what he means by multiple shot. Does he mean more than one shot?
More than one shot? I think he means the actual gun with charges loaded instead of a single shot.
Oh, so you're looking at a triaxial test. Okay, so you can have a block test where you have, a large block of outcrop rock, and you can shoot a small gun section under confinement and pressure in a big block test. That's a limited availability and extremely costly, probably, but that is certainly a good way of doing things. Added value, minimal, I would say. Yes, it can be. If you've got a lot of time and a lot of money to do a lot of shots, then certainly a block test could be nice to do. The real added value I would suggest in general be fairly low. It depends on your real conditions where you see the value in this adding to your knowledge of how the reservoir will perform, how the perforation will perform in your simulated reservoir conditions. I guess that's what he's talking about, is a block test. Is that what you think, Carlos?
I think so. I think so.
Okay.
Very good. No, thank you, Mark. It's 1 minute to close. So I would like to say a few words. I would like to thank you, Mark. I really appreciate you stepping up for the first webinar. It was very good session. I would also like to thank Eliana, who helped us a lot to put this together. I really appreciate it, Eliana, all the effort, and all of you participants that joined today. We are planning our next webinar in the upcoming months. Right. So stay tuned through the IPF website, through your emails and LinkedIn. So we'll publish there when the next one will be with the topic. So this closes our webinar. Thank you again for joining, and have a great day.
Thank you all very much for joining, and please excuse my wife for wandering around in the background, wondering when she's going to be taking to the ski slopes.
No worries, Mark. Thanks a lot.
Bye. Thank you all.
Bye-bye.
Thank you. Bye.